Hi everyone, thanks for coming. So today I'll be presenting this paper. The algorithm that we present here is called the Deep InfoMax, and it was accepted as an oral paper at the International Conference on Learning Representations, ICLR, this year. So that's going to happen next month. About me, my name is Karan. I'm a graduate student at the University of Toronto, and this is work that I did while I was an intern at Mila in Montreal. And feel free to jump in if you have any questions at any time. Let's make this interactive.
The mic's not working.
No,
It is. It's not for you.
Can you speak up?
Yeah. So these are my collaborators on this paper. So Devin Helm is is currently an adjunct professor at Mila and also a researcher at Microsoft Research. Phil Bachman and Adam Trishler also helped out. They are also researchers at Microsoft. Alex Fedorov and Samuel Lavoie are graduate students, and Yasha Benjio is a professor at Mila. Okay, so this paper is about representation learning. Overall, I'm going to talk about what representation learning is, why it's important, why we need it, how we can learn representations by maximizing mutual information, which is exactly what the algorithm proposes. And finally, we'll talk about how we evaluate these representations to figure out if we've learned good representations from our data. So in everything I'm going to talk about today, we're looking only at images. Of course, you can learn representations from text, from speech, a lot of other modalities, but here we're just looking at images. Okay. So why do we want to learn representations? Raw data is often not very helpful, okay, many times. For example, if you have an image, it's just represented as a bunch of pixel values, right? And so if you want to perform some downstream tasks, such as classification, figure out what's in the image, those numbers aren't really helpful. So what you want to do is extract the information from that image to figure out what's in that image, right? So that's where learning a representation comes in. Taking that low-level data and learning some high-level representation. You can also think of it as a low-dimensional summary of the data. Usually the representations you learn are a lot lower in terms of number of dimensions than your original data. Right? And as I said, you can use this for tasks later on, like classification. And also, usually, when there's some sort of pattern in your data, such as say you're doing some sort of clustering task, usually you'll find that the representations that you learn can help you discover some sort of structure in your data. Okay. I like this example because say you have a bunch of your raw data right on the left, and this can be a very high dimensional space, and so it's usually all scattered. At first glance you don't know how to make sense of it, but then once you map it down, say to a lower dimensional space, usually you extract the features that are useful for whatever downstream task you want to perform. And in this case, maybe it's classification, and in this case, it's even separable. So that's how that's the whole aim of learning representations. Okay, so now that we've talked about that, what is a good representation? I like this quote that was in this review paper on representation learning from 2013. It says that a good representation is one that captures the posterior distribution of the underlying explanatory factors of the observed input. Now that's a very loaded sentence, but what does that mean? So say there's probably some features in your data that are indicative of whatever task you want to perform, right? Say you want to do a classification task on an image. It's probably the pixels that are closer to the middle of the picture that are going to be useful for you, right? So those are the ones that are going to help you capture that posterior distribution for whatever task you're doing, as opposed to the ones in the corner of your image, which probably won't be very useful at all. So what we're concerned with are two factors in terms of learning representations. So high mutual information with the input, meaning that, we'll talk about mutual information in a bit, meaning that you want your input to have to be highly correlated with the representation that you learn. But we have to be careful there because in terms of pictures, in terms of images, you have a lot of pixel level noise, which isn't really helpful to the task you're trying to perform. So you don't want to capture that information. So you have to be careful about what information we're capturing. And at the same time, we want it to follow. We want our representations to have certain statistical properties. Separability is nice, although we don't necessarily need it, like I showed you in the last slide. Independence is an important one. Say you map your data down to 50 dimensions. You don't want only 5 of those features to be useful, to carry information, right? Like if all the other dimensions are just some combination or some repetition of your original 5, then really you're only learning 5 dimensions worth of features, and the rest of it is really redundant data. So you want independence in your dimensions. That's something that also that deep InfoMax also enforces, and that is a statistical property that we would want. That way, given your constraint, how small your representation is, you're capturing the maximal amount of information. So high-level overview of our algorithm. So what we do first is we take an image, okay, we map it down to a feature map. So that's that thing over here. I can use a laser actually. That's this thing over here, an M by M feature map. These are all patches, not pixels. We'll come back to this later. We compute the representation, which is this guy y, just a feature vector. And so we call these our positive pairs. At the same time, we take another image, all right, which is totally unrelated. We map it down to its feature map, and pair that up with the same feature vector that we had from our original image, and call these our negative pairs. And then, I hope you're all familiar with generative adversarial networks. So we train a discriminator that has to tell apart your positive examples from your negative examples. So the discriminator is looking at 2 inputs, the feature map and the vector, and trying to tell if the feature vector is a representation of the feature map. Why we're doing this will become clear in the next few slides. But this is a high-level overview of how the algorithm works. Okay, so I've talked about mutual information a bit, and now here's exactly what it is. So given 2 variables, x and y, mutual information tells you how indicative one variable is of the other variable, right? So this is the definition of independence of 2 variables, which means that the probability distribution, the joint probability distribution of x and y is equal to the product of the marginals. Intuitively, that's saying that if I have x and y, and I can sample from x and sample from y, and I know their behavior, and that's the same as sampling from their joint distribution, then knowing the joint, then that means like they're not really correlated, because knowing the joint distribution doesn't tell me anything new that I can already find out about them independently. So that means that they're totally independent. So the mutual information would be 0. So what we want is to actually maximize this value, so that one variable is always indicative of the other variable. So that's how mutual information is defined. This is also, by definition, the KL divergence, or Kullback-Leibler divergence, between the joint distribution and the product of the marginal distributions. So we're trying to maximize this divergence right here. That's okay. Here's the setup for deep InfoMax. So we have an encoder. Okay, an encoder parameterized by psi, and that is so it comes in 2 parts. First, you apply f, then you apply h, and we'll see why that's useful soon. So it takes images x, so x is the image space. It takes an image x and maps it to a feature map, f of x, and then that's further mapped to y by applying h. So that's the encoder. It's taking an image, it's mapping it down to its representation, y. The distribution over the y's is called the push-forward distribution. So basically, if you just take all your images x, and then you push that through the encoder, the distribution that you end up with is called the push-forward distribution. And so that's given by q psi x. This is just a setup. Now the objectives. We have 2 objectives that are happening at the same time. First, you want to maximize mutual information between f of x and y. So not x and y, but between f of x and y. Because remember, x is just the image. F of x is a feature map, which we'll talk about next. So between f of x, between the feature map and the representation, we want to maximize the mutual information there. At the same time, we want to match the push-forward distribution, so the distribution over the y's, to a prior distribution, q prior. And that's similar to how adversarial autoencoders or even variational autoencoders work, right? They're forcing that representation to match a certain distribution. So these are the 2 objectives we have. So the encoder, which I talked about in the last slide, it looks like this. So you have an input x, which is the image, and we map that down by performing a bunch of convolutions on using a neural network. That's very standard, to an m by m feature map. you should know that this m by m, the m is not the number of pixels, it's patches. So you take so you can think of each block there as being a bunch of pixels, right? So you have like a part of an image basically, and we'll see why we do this. Why we do this? It will become clear very soon. So that's f. That's what f does. F maps the image to the feature map. Next, we have, so that's after we've done all the convolutions. Next, we have simple fully connected layers that map that feature map onto the representation y that we want to learn. So we go from x to f of x to h of f of x. And in all our experiments, we used a 64-dimensional representation. Okay, and so just again to clarify, we're maximizing mutual information between the feature map here and the representation here. So this just becomes a neural network problem, standard neural network training, and so we have a loss function that we optimize using standard methods like gradient descent and atom. So remember, a few slides ago I showed you that the mutual information can also be written as a KL divergence, right? And one property of KL divergences is that they have this tight lower bound, right? So here you have, say for two distributions P and Q, you have over all functions T, you have this value. So you're maximizing T on samples drawn from P, and you're minimizing T on samples drawn from Q. Right, so once you have this optimal function, you basically have a tight bound on the KL divergence. And this is really helpful because if you think back to the setting of GANs, you have this function that's trying to maximize values, maximize its output on values drawn from one distribution and minimize its values from another distribution. So we can frame maximizing mutual information as an adversarial training problem. So this is I should just state that this is a theorem by Donsker and Varden, two statisticians from back in the 80s. So now that we know that, we can use this. This is very helpful to us. So we parameterize a discriminator. And that takes in two pairs. That takes in a feature map, f of x, and a representation vector y, and maps it to a real number. And what it's trying to do is tell that is this feature map and this representation pair, or is the representation is it the representation for the feature map, or are they totally independent? That's the whole objective here. So we're maximizing basically this guy over, which just becomes this whole thing right here, right? So we're maximizing T on X pairs drawn from the joint distribution, and we're minimizing it on values where you draw from Px until the Px meaning like you have another sample, but it's just the same distribution. It's just two different samples. Good to go? Good to go? Okay. So we'll back up just a little bit. So here we have this tight lower bound on the KL divergence, and this helps us really. And remember, like KL divergence is a definition of the mutual information. And mutual information can be written as a KL divergence. So when we rewrite it like this, all we're doing is we're able to turn mutual information maximization into an adversarial training problem, which now is a very popular thing. So we have no problems dealing with that. So T is a discriminator network, basically. It just takes in two inputs. So one is the feature map, f of x, and the representation y, and it's outputting a real number. If based on how confident it is that feature map and that representation are a pair that go together. So that representation is actually is a representation of the feature map. Okay, and so we want to maximize this value. We want to maximize this guy right here. So this becomes our objective. We're maximizing over parameters omega and psi at the same time. So we just do this iteratively using an optimizer like atom. Okay. So here's how the algorithm actually looks in practice. So we sample our positive images. So we call these positive from our distribution of images Px. Okay. And we compute the feature map. So this is just the first part of the encoder. We compute the m by m feature maps. So this is f of x for all our examples. Next, we compute we compute the actual representation. So that's y, all right? Then we pair those together, right? So those are our positive examples. Those are the positive pairs. Then we do the same thing, but we do it to create our false examples. So we sampled from the same distribution, except these are different images now, and we compute their feature maps. And we pair them with the y's, but remember, here's the important thing, that this is f of x negative, right? So these are negative examples drawn from here, but these y's were computed up here. So these pairs don't go together. So these are negative examples. Then we maximize this equation, which we've already seen now. It's just the same as on the last slide. It's the lower bound on the KL divergence. And so we have the positive pairs here and the negative pairs here, and we iteratively optimize. That's what the algorithm looks like. Again, just to get a visual representation of what's going on, we have the m by m feature maps, and then we have the actual representations. We pair those together, so these two pairs go together as positive examples, and then this guy right here goes with the feature vector as a negative example, and we just put that through a discriminator and train it to optimize. Okay. So that's in a sense what Deep InfoMax does, and we called it Global InfoMax. The last few slides were titled Global InfoMax for a reason, because we realized that we might have a problem. Okay, so when we put an m by m feature map together, which is supposed to summarize a whole image, together with a representation, it might capture. We hypothesize that it might only capture global information, right? That's shared across the whole image. And many times this is like pixel level noise, right? Rather than local information, because maximizing, doing our objective that we had in the previous slide, it's not encouraging our encoder to capture information that is local to particular parts of the image. And many times we want to do that, because many times we have certain parts of the image that are useful, and then certain parts of the image that are not useful. So we have another approach that we call local InfoMax that I'll talk about next. So remember, we had this feature map which had m by m patches, right? And m is not the number of pixels, but it's like a sub image within the image, right? So what we're doing now is we're maximizing mutual information between the representation like before, but now not with the whole image, but with a certain patch of the image only, right? So for one of these guys, before we were maximizing the mutual information between this whole thing and our representation y. Now we're doing it. Now we're doing each individual square together with y, and that's exactly what this objective right here is. So we're taking mutual information f of x sub j being the jth patch, and together with the overall representation of x, and we're just summing it over all patches. So it's the same objective. You're doing it patch-wise. And how this works, and so I mean, I should say that the hypothesis here is that once you do it with a certain part of the image only, whatever information is in that patch, it's going to force your encoder to capture that information and put it into your representation. So that's the whole motivation behind doing it this way. So the algorithm is actually very similar to the algorithm from before, from Global InfoMax. So you sample the positive images, the positive examples, and compute their feature maps, and then you compute the y's for those. And you call these your positive pairs, except now you have the subscript j here, right? So you're doing this for all j. So your positive pairs have just blown up by a factor of m squared, because you're doing it for each patch now. At the same time, and you do the same thing for your negative pairs, right? So you compute patches. So you have patches of another image, and you pair those with the representation of your original image, and you just put this through the same objective. So you have your positive pairs and your negative pairs here. Okay, that's local InfoMax. And
Can you go back?
yeah.
Can you, go through this one more time slower?
Yeah. Okay. So we're sampling positive images. These are positive examples. So it's taken from our distribution over images, and we compute the feature maps, the m by m feature maps, right? For all our examples. Then we compute the representation for that by just putting those through the rest of the encoder, okay? And so now we have our feature maps in our representation. So we take each patch in that feature map that we have and pair it together with the representation. And these are our positive pairs because those actually go together, right? Now we do the exact same thing, except we're taking some other images, okay? And we're pairing those with the representations that we had computed up here. So those are negative pairs because that patch and the representation, they don't go together, right? And then the objective here is just a lower bound on the KL divergence, and so we're effectively putting in our patches, putting in our positive pairs here and our negative pairs here. And by maximizing this, you can see that like we're trying to make the value of t really big on these positive pairs. And since we have this negative sign here, we're making the value of t really small on these negative pairs.
So you don't have just one representation now. You have a representation per batch, right?
No. So
Per patch. No?
So you still have one representation, but when you do your optimization, you're maximizing the mutual information between that patch and between the representation and the patch for all the patches. So you have that representation paired together with m squared patches. Is that clear? Okay. Yes.
So just to be clear, what do I's index and what do J's index?
Okay, I's index that's a good question. I's index the examples. So we do this batch-wise, right? So they index these guys, and the J's they index the patch. Yeah. So I just put a subscript. Where is it? I just put a subscript J here because like which column or row it doesn't really matter, right? Like if you're trying to do implementation, then yeah. But like here's just to get the idea that this is one patch of the image. Yeah.
So compared to the previous slide where you're talking about the global, so the main difference is that you're using patches here, right?
Yes.
So in terms of, I don't really get why do you call this local? Like when you're using patches.
Because when we had the global algorithm a few slides ago, which looked very similar. You looked at the whole feature map and the representation, and you're maximizing mutual information between those two, right? We called it global because we found that it's actually encoding more information that is shared across all patches of the image, right? That's why it's global. But this is local because you take one part of the image, or like once you map it down to a feature map, you take one part of it, and then you maximize the mutual information between that part of the image and the representation. So it's forcing the representation to capture information that is local to that part of the image only.
So the discriminator goes through each patch.
Yeah.
Could you repeat the question?
So the question was, does the discriminator go through each patch? I mean, it goes through each patch in the sense that it looks at each patch together with the representation. Yeah.
So if you're having, for example, data set, some of the features that are not, you don't want to capture those features, but they're very like repeating, across the data set. There are certain you pick that as the local features, right?
So that's a very good point. It does that, and I think, yeah. So the question was that if there's some, let's say, noise that is repeated across the image, but it's not very useful to the information that you're trying to capture in the image, isn't that something that this is going to pick up? And the answer is yes. It is exactly going to do that. And in fact, I have an example later on that talks exactly about that. So that's good. Okay. Any other questions, comments? Okay. The diagram is just like the diagrams I've shown you before. We're taking local feature here just means a patch, right? So that's just terminology that was used. Together with the representation, and we're putting those through the discriminator. Similarly, we're generating patches for another image, pairing those again with the representation and putting that through the discriminator. Okay. It's the same algorithm that I showed you on the last slide. It's just a visual representation. Okay, so I've shown you global InfoMax and local InfoMax. The other objective is matching representations to a prior. So we have this representation Y, and we want it to match some distribution, Q prior. This is the actual push forward distribution over the y's. And how we do this is we set up another neural network, D, parameterized by theta, that takes representations and maps it to a real number. So it's just telling you, if I have a bunch of samples from in this representation space y, how confident is the discriminator that it came from Q prior, came from the prior distribution as opposed to the original distribution? And this is I think this is a setup that we've seen many times before in like adversarial autoencoders and GANs. So it's really so you have the discriminator that's trying to maximize this value. So we use the Jensen-Shannon divergence here. It's trying to maximize the Jensen-Shannon divergence between these two. And while we are trying to make our pushover distribution match that prior, so we're trying to minimize this value. So we're iteratively updating the encoder to also try to to map it onto a certain distribution. And I should say that in our experiments, we found that a uniform distribution in our representation space ended up working much better than a Gaussian distribution. So that's what we used here. Because typically, I think when you have like adversarial autoencoders or variational autoencoders, people have used Gaussian distributions, but that's not what worked best in practice for us.
Do you have any intuition why?
So the question was, is there any intuition as to why for us a uniform distribution worked better than a Gaussian distribution? And honestly, I don't. But I think what might be a factor is that in a lot of these algorithms, what you're doing is you're just your objective is reconstruction loss, right? Whereas here, there's no decoder, right? You have just had the encoder. So the encoder is trying to do multiple things. It's trying to maximize mutual information and also match this prior. Right, so maybe it's those competing things that the encoder itself is trying to do that might cause that might be a reason as to why the uniform works better than the Gaussian. But that's still not an explanation as to why it would work better. Okay, so now putting everything together, we have the global InfoMax, right? So information maximization between f of x and the encoder output. So encoder of x is just y, right? And then you have the local patches. So now you're summing over all j patches. You're maximizing mutual information between that and your representation. And then you're trying to match the push forward distribution to a prior. And here we use three hyperparameters, alpha, beta, and gamma, just to weigh each objective differently. And so we just tune these empirically based on what works best. Yeah. Sorry?
What were the ratios? What the relations between them?
What were they? So we have, it depends. So we ran a bunch of different experiments. So sometimes you wanted to only consider the global InfoMax algorithm. So you wanted to set your beta to 0 basically. Sometimes you wanted to only have the beta and set alpha to 0. And we found that in both those cases, the optimal gamma value actually changed. So. Okay.
Question. For the hyperparameters, you said one time when it's alpha low. So is there a use case why you use that when alpha is low and beta is higher?
So
is there
what we found was that
the hyperparameter that works for specific cases better?
So I think this is something that based on, usually it's based on your data set, that the hyperparameters will always vary, right? So there's really no principled approach to figure out what should go.
When the global InfoMax is higher as a weight compared to the others, or you haven't.
So I mentioned that when we set, so we tried both alpha equal to 0 and beta equal to 1, and alpha 1, beta equal to 0, and in both cases the optimal gamma that we found was different. Right, which is not too surprising because you're really doing different things in both cases. So, does that answer your question?
So which is the better performance? So the best matching of the hyperparameters. Better. I don't know. Based on the data set or.
You're asking which?
Yeah.
What are the optimal values?
Yeah, optimal values.
Oh.
Yeah. Based on your experiments.
Based on our experiments, we'll talk about this in the next few slides, but usually when alpha is 0, we've actually found that that's actually best, which is surprising. That was not expected. Anyways, okay, so only a few more slides before our official 5-minute break. So we've been using the Donsker-Varden bound as our objective so far, but in practice we can actually use some other values too. So both the Jensen-Shannon divergence and noise contrastive estimation are both other things that we can maximize instead of using this bound here. And the good thing about these two other objectives is that you can set it up the same way so that you can use a discriminator, right? And so, because right now the whole benefit of using this bound was that you have this function that you're trying to maximize t, and that's how you can set it up as an adversarial training problem. And you can do the same thing with the Jensen-Shannon divergence and noise contrastive estimation. And there are also these other metrics that you can also set up as an adversarial training game, but we did not try those. So we found that actually Jensen-Shannon divergence actually works best in practice and we'll talk more about that in the results. And then these other two, so the Donsker-Varden bound and noise contrastive estimation, they tend to be more unstable when the number of negative samples that we use, number of negative pairs, is low. So we'll talk about that.
But it obviously would be faster, right? If you use NC, for example, as opposed to KL divergence.
NCE works better than the first one. So we never explicitly use the KL divergence because we always set it up as an adversarial training game.
With the same number of negative samples, the NC works better than.
Yeah, with the same number of negative samples.
And does it run as fast?
Sorry?
Does it go as fast?
You mean does it converge as fast? I'm actually not sure if it converges as fast, but I would assume so because the performance is definitely better.
So would you negatively sample differently for NCE as compared to Dunstan?
Yeah, slightly differently.
So less number of negative samples or?
Well, in the first one, we usually use the same number of negative samples as positive examples, but in NCE, I think the way it's like in the literature, when you use noise contrastive estimation, you're supposed to use a greater number of negative pairs than per each positive pair that you use. So that's why, yeah.
When you say you only use few negative samples, could you give us like an idea about the ratio?
So when we use only a few negative examples, the question is when we use only a few negative examples, what is the ratio for number of negative examples to positive examples, right? So so usually when the standard practice when you use like the first one is to do a 1-to-1 ratio, but I think in noise contrastive estimation you're supposed to do more. And we actually tried experiments where we varied the number of negative examples, and we found that as you increase them, the performance really got really good. So the Jensen-Shannon divergence here performed the best in terms of the downstream tasks we wanted to do, and we found that actually I think it's in the order of like 20 or something that that noise contrastive estimation performed as well as a Jensen-Shannon divergence.
Because in the cases that you're dealing with very noisy data set,
Yeah.
and at the same time you want to do some sort of.
Could you speak louder?
Yeah, so in the cases of when you're dealing with noisy data sets and then you want to do anomaly detection, I think the distribution that you get at the end, for your output, it's going to be very unstable in terms of, if you run any kind of investigation and stuff, you might not get very good results. So I was wondering,
You're saying you'd get better results as you use more negative examples.
Yeah.
Yes, that's exactly what we found here. Yeah. Yeah.
I think that's one of the problems is encoding in it. But you don't have decoding yet.
There's no decoder.
Yeah.
Yeah.
What does undesirable statistical
Can you use the microphone because they said
What are the undesirable statistical properties?
Right. So when you have, say you're trying to match two distributions under a KL divergence, say you're trying to match a distribution Q to a distribution P, when Q is very large at one point and P is very small, your KL divergence will be very big. It'll blow up. But in the case of the Jensen-Shannon divergence, you're taking basically two KL divergences, right? And they're both with the average distribution. And so it's not going to be your divergence won't be as large because your ratio will be a lot smaller. So that's what I mean. So that's, yeah, okay. So we just talked a little bit about noise contrastive estimation, but just to go into more detail in it, this is the one of the 3 objectives we used. So the idea behind noise contrastive estimation is that a good model should be able to tell apart data from noise, right? And if any of you are familiar with like Word2Vec uses noise contrastive estimation, right? Because you're trying to minimize the distance between 2 vectors whose words appear in the context of each other. At the same time, you maximize the distance between 2 vectors whose words do not appear at the same time, right? So you're taking your actual data and then you're taking noise and you're trying to push down on the noise, push up on your good data. So this is a paper that was at NeurIPS last year, and they basically are doing, and so using their approach, using noise contrastive estimation with MI, we basically have this objective that we also tried in deep InfoMax, and it looks very similar to the first equation I showed you with the Donsker-Varden bound, but it's slightly different because here we have this first expectation runs over the whole thing, and we usually tend to use more negative examples. So it's similar, but not quite the same. Okay, and that's the algorithm. So we'll take a 5-minute break now. Question?
Okay, so I'm kind of interested in the optimization algorithm you use. Did you use the one that is similar to VAE and AAE, or use the one similar to TS&E?
So those are both, they both have a stochastic component to them, right? Because in a VAE you're sampling, right? Here there's nothing like that. So
you're similar to TS&E.
TS&E is also, actually I'm not too familiar with the optimization algorithm for TS&E, but I know that it's a completely stochastic algorithm, right? So
it is, but it is kind of optimizing the distribution itself.
So TS is mostly used for visualization purposes, not necessarily optimizing it.
Well, okay, let me rephrase my question. Did your SGD algorithm optimize the distribution directly using reparameterization trick?
No, there was no reparameterization trick here. So
how did it work?
So I showed you. Let's go back. It was trained basically like a GAN, right? So let me show you. Okay.
So basically, you take an image and mix a noise on top of it.
No noise needed.
So okay.
So I mean, like we want to optimize this divergence, right? We want to optimize a KL divergence. We want to maximize it. So we found a lower bound on it, which can just be, and so this uses this lower bound requires that your function t be the function that gives us the supremum value over this part here. And so the way to do that is just to use adversarial training to get a function that gives the maximum value over one distribution and the minimum value over another distribution. That's just like how a GAN works. So we set it up as adversarial training. So I hope that answers your question.
Well, probably because I don't understand the algorithm good enough. The way I see it, if you try to maximize the KL divergence, then you need to have 2 distributions first.
Yeah.
And instead, in this case, you just have 2 images where you can add all kinds of noise on top of it.
So we do have 2 distributions, and the 2 distributions are the joint distribution between our image and representation, and then the product of distributions between the 2. Right, so we're trying to maximize the value over the joint distribution. The joint being you take an image and then you encode it, right, to a representation, and then you maximize you try to maximize the discriminator output on that pair, and you're minimizing over the product of marginals. The product of marginals being you take your y, but you take an x that is from a different image. You take a different image, and then you're putting those 2 together. Those are the 2 distributions in this case. Yes, question?
This kind of a comment and a question. Just that this paper reminds me a lot of deep steganography, and I was wondering if
What's it called? Deep what?
Deep steganography. And so, if you're taking two images and you're encoding a secret image inside an image that exists, how do you pull out the secret image? But philosophically, sort of, I was wondering, how do you find an image that isn't necessarily there? What could be conceivably encoded in that image? Is that sort of approximately what?
So you said an image that isn't there, right? I mean, it is an image that exists. Both the images that we use for the positive example and the negative example are both taken from our actual set of images. But it's just that when you pair them up with the representation, you only have one representation, and that's for your positive example. If you're pairing up also your negative example, the image, you're pairing up another image with your representation, and that's a negative example because that representation does not correspond to your image, to your other image. Does that?
Yes.
Okay.
About the batch size, how did you come with the right size, the optimal size for the batch size? And what is the impact on the optimization on a wrong batch size?
So I think, if I remember correctly, we use batch size 64 just because I think that is very standard right now. Most people in deep learning use 64 batch size. But if you use a smaller batch size, I know that your gradient that you use in optimization, usually that's always an estimate of the true gradient because you never have the true gradient because you never use the whole data set, right, to compute the gradient. Your gradient will be less accurate if you use a smaller batch size.
Sorry, batch size.
Oh, patch size. Oh, okay. Totally missed it. So it's about patch size. So we used patch size 7 by 7. So you have 7 patches by 7 patches, and each patch was 3 by 3 pixels. So you have a total number of 49 times 9 pixels. That's the feature map we reduced it down to. We didn't try too many patch sizes, so I can't really say what would happen if we varied it. But intuitively, I think it might be better to keep the patch size relatively large, so you're not doing too many operations on it, just so that it's not too far removed from your image, right? Otherwise, you're performing more arithmetic on your patch size, so you could be getting 2 images to conform to one patch, even if they're not the same, right? So you want to keep it relatively close to your original image. So, yeah. Question.
So can we move on to the results of the selection? Circle back.
Yeah.
That's the last question.
Yeah.
Okay, last question.
I have 2 questions, actually, so ask the question.
Can they wait until we finish, or like go through the results?
Clarifying questions. So one question here, when you have this like log of expected value of e to the power of t, and you're using one discriminator, so always you use only one sample group, so that expectation is calculated for one sample only?
So in practice, to compute the expectation, we do it batch-wise, right? So you're taking a sum, you're taking an average of the discriminator value over a bunch of examples.
Yeah, so when you have your discriminator now, like as t, you have one input and bunch of like negative samples, and you calculate the average of those, correct?
Sorry, so you said you have one.
So you have your positive sample and bunch of negative sample, and then you take an average of those like outputs.
So the positive pairs are all here. So we're only taking the average over the negative pairs. Yeah.
And the other one is in the prior match, you use again another discriminator, or how do you use that?
Yeah, that's a different discriminator.
So you have 2 discriminators.
Yeah. But this discriminator is only telling you if a sample in our representation space is drawn from a distribution or not. Whereas the other discriminator is doing a completely different job. It's looking pairwise at things, right? So yeah. So there are 3 neural networks set up in total. 2 discriminators and 1 encoder. Okay. Let's move on. We good? Okay. So now we'll talk about results. So the main question is, how do we evaluate the representations that our encoder learns? So one way to do this is classification. So classification on the representations. So if you can train a classifier that will get a higher performance on the representations that you learn, then intuitively then you've learned a better representation, right? So we tried both linear classifiers such as support vector machines and also nonlinear classifiers. So a simple neural network with one hidden layer to perform classification. So we did this on a bunch of data sets like CIFAR 10, CIFAR 100. So these are data sets where there are actually class labels. So once we learn the representation of the images from those data sets, we use a supervised learning approach where we take those representations as input and try to match it to their class label. That's what we train the classifier to do.
Do you try with nearest neighbors?
Sorry?
Do you try with the nearest neighbors?
With the what?
Nearest neighbors.
Nearest neighbors?
Basically we'll say like everything was put together, everything that belongs to the same class was put together in the representation space.
We did a nearest neighbor analysis to see like what it was clustering together, but we didn't actually use it for classification purposes, right? So, because in the case of
I mean, this is basically saying like you can separate them by planes.
Yeah. So nearest neighbor in theory it should work, right? Yeah, we didn't try that though. But there is one result slide I have about nearest neighbor analysis. So classification on CIFAR 10 data set using a support vector machine. We use the representation. So DIM is our algorithm, Deep InfoMax, and we also tried classification using the representations learned by our algorithm, and also compared it to the representations learned by other algorithms. So these different columns represent where the representation was taken from. The one that we're most interested in is Y being the 64-dimensional representation that our encoder outputs, and we can see here that the DIM with local only. So we have the local only objective, meaning that the hyperparameter in front of the global objective is 0. We see that actually achieves the best performance overall when you take the representation from here. But when you take the representation from other layers, actually, it looks like with the local only objective, the classifier accuracy is the highest here. So that's a good starting sign. By the way, these other columns are, so this first column here means that we took the output out after the last convolutional layer and in our encoder, and FC meaning we took basically the layer before it output Y, and before we did the well there's no softmax because we're taking representations from an encoder, right? There's no encoder So that was using the SVM. Now we tried it on linear neural net, not linear, but like on small neural networks too, with a single hidden layer. So we tried it on CIFAR 10 and CIFAR 100, and again, you can see that basically, to summarize what you see in this slide is that Deep InfoMax blows everything else out of the water. So it's performing, so that the classification is going well on these representations. And again, I think when we use a local objective, it performs a lot better than the global objective, right? So we saw that in the last slide too. So, yeah. So that's classification. And so now we have Tiny ImageNet and STL10, 2 more data sets, and you basically have the exact same story going on here. I think when you have local, let's see here. Yeah, it's basically doing the best. Yeah, okay. So that's classification. That's one way to evaluate the representations that we've built. But there are other ways too. So there was a paper that came out last year where the authors, what they do is they basically, they figured out a way to estimate the mutual information between 2 variables using a neural network. And so we try that here with our patches, with our feature map and the representations that we have, trying to estimate the mutual information between these 2. And so we can use a neural network to do that. It's called MINE. And so that'll give us an idea of how whether we're really achieving our objective, right? The other one, this one is actually one that I really like, is called the neural dependency measure, right? So remember earlier when I talked about our objectives in representation learning, we want to find features that are all independent, right? So we want all our features to be independent so that you're not capturing the same information over and over, but you're encoding the maximum amount of information possible in these 64 bits that you have. So what neural dependency measure does is it tests exactly this. So say you have your representations, right? So each row here corresponds to the representation of an image, right? So you have so this is like this is the batch axis here. So this is one representation, this is another representation, and so on. What we do is we take this sort of this matrix, and then we shuffle it we shuffle it column-wise, right? So what you're doing is each example has basically does not exist anymore because you've shuffled the columns, and then you put this into a discriminator, and it's trying to tell apart the real examples from the fake examples. And so if that's not clear yet, I have a diagram to illustrate. So say you have a bunch of independent representations, right? So if they're independent, say they're drawn from a Gaussian, for example, right? They'll look something like this, right? Whereas if they're dependent, usually there will be some correlation between one variable and another variable, which clearly you have here. You have this sort of best fit line that I can draw, right? So these representations here are dependent. And so then if I were to take this matrix here and shuffle it feature-wise, right? Then what I would get is shuffled representations that look something like this, right? And so it's very easy for the discriminator to tell apart the original pairs, the original examples from what you've shuffled. Whereas if I have the independent, if I shuffle the matrix in the independent case, you'll really get something that looks the exact same. So the discriminator, it can't tell apart the shuffled examples from the real examples now. And so now you train a discriminator to tell the two apart, and the harder it is for the discriminator to tell them apart, the more independent your samples are. So that's the intuitive idea behind neural dependency measure. So we looked at representations from all these other state-of-the-art algorithms and also deep InfoMax to see how they've performed.
Can I ask two clarification questions? Could you go 2 slides back? There you go. So first of all, the first one, is that, which encoder is it? Is it the encoder that you trained for your own system? I'm trying to understand. Okay. And excellent. Okay. The second one, I forgot what I wanted to ask.
Okay.
You're welcome.
So to check how independent our features are, the higher the value here, it means the higher the loss of the discriminator. So we can see that the deep InfoMax had the highest scores. So we're learning features that are quite independent, right? And at the same time, we found that BIGAN, which is a recently proposed algorithm too, is doing a very similar thing. Is also learning independent features. It actually seems like it does better here than all of deep InfoMax. And then the neural dependency measure, the higher the value, the higher the mutual information between the input and the representation. So here we found that our values are the highest, I think. No, only this one is the highest when you have both local and global only. So
which that was the question. So which discriminator you're using for your second method, neural?
So that's a different discriminator. That all it has to do is has to tell apart your representations from another set of representations where all you do is shuffle the features.
So you train it separately?
Yeah, that's totally separate. That's just for evaluation purposes. You don't need that in the training or anything. Yeah. Okay. The last set of experiments were totally different. So occlusion is, given an image X, you randomly occlude part of an image and call this X prime. So basically you're just blocking off part of an image, right? So you take all these images and then you just block off part of it, right? And then the goal is to maximize the mutual information between the representation that you get when you pass that through the encoder, right? So now you're computing this representation Y prime by passing through this image, which has part of it blocked off, and the actual patch of the true image. So when you compute this patch here, you're not occluding anything. You have the whole thing, and so that's one example to see. That was one example. That was one test case. Another one is coordinate prediction. So you're given a representation, and part of the image was originally occluded, right? And you're trying to see you're trying to maximize the probability of which patch this belongs to really see is the representation that you're learning, does it really cohere to like understanding locality, right? Because if you can figure out where in the image this should be, it's understanding local features. And we found that in this case, so we only tried the experiments on both occlusion and coordinate prediction for deep InfoMax. We didn't try it against any other models, because I mean and then we found that when you're actually occluding parts of the image, the classification, or rather the classification accuracy, once you have these representations. So I should say that we're doing classification again on CFAR 10, CFAR 100, but the representations were occluded, and we find that when you occlude and then you maximize mutual information between the representation and parts of the image locally, it actually performs better than if you were to just use the original algorithm. And the intuition here is that when you look at part of an image, and when you look at a patch of an image and the representation, where the representation originally contains no information about that patch, because the representation when you passed it through, that patch was occluded. When you try to maximize the mutual information, it's gaining all that information about that patch, and it seems like it actually does a better job here than when you use both global and local objectives. So that's why this one seemed to have performed better. Yeah. Question?
Was that a replacement for the image, or was it used as well? Like so if you had the image of the car, for example, would you use the full image and the occluded image, or only the occluded image in that case?
So the question is, do we use both the full image and the occluded image, right? So when we compute the representations, originally we compute a representation using the occluded image. So X prime here is the occluded image, right? And then we have the actual patch of parts that were originally occluded, and we maximize the mutual information between that representation and those parts that were occluded. So that's what's happening.
Thank you.
Okay. Okay. So that's clear. So Felipe is gone now, but he mentioned nearest neighbor analysis. We did a nearest neighbor analysis where we took a bunch of pictures, and then we looked at what the nearest neighbors are in the representation space to that picture, right? And we found that when you have, so all these, this batch right here is when we have the global only objective. So we're not doing the local optimization. And here we're not doing any global optimization. So we found that when you have an image, its nearest neighbors in the representation space tended to be more coherent when we did local only optimization, right? So you look at, what's a good example here? You look at this guy right here, right? Sort of like, so it's kind of an animal or whatever. And then you look at the nearest neighbors, and when you use local only objective, you're getting these types of things, right? So something that's like relatively related. Even if this is not an animal, it still kind of has the same colors maybe. But then here, it's, okay, so it's not great, but then here it's completely random. Like these things are, I don't even know how these are related to each other. I don't even know how to chain those together, right? So the neighbors, the takeaway here is that the neighbors that you have are much more reasonable when you do the local only objective. The representations that you learn, their neighbors are much more reasonable with the local only. Population studies. So I think you asked about the number of negative samples, right? So then, so this is another test that we did when we have the different objectives. So the Jensen-Shannon divergence, noise contrastive estimation, and the Donsker-Varden bound. How is the accuracy based on the number of examples? So the number of negative examples is actually given on a log scale here on the bottom. And this is the classification accuracy. So we can see that Jensen-Shannon is very consistent, right? And so you can basically use a 1-to-1 ratio, and you're going to get good accuracy with a Jensen-Shannon divergence. Whereas noise contrastive estimation relies on a lot of negative examples, and then this one, the Donsker-Varden bound, is even more unstable in practice, right? Actually, this one we saw that this one had the highest variance across when you run it across multiple experiments. This one had the highest variance, so it tends to be very unstable. Sometimes you can actually get a better accuracy with low number of negative examples when you use the Donsker-Varden bound compared to noise contrastive estimation, but it's just because it has such high variance. Yeah. This is the accuracy when you do classification on, or it doesn't say which data set.
When you have very small negative numbers, I think maybe if one measure would be better in terms of accuracy.
Why?
Because like, let's say that if you have 100 images and then you have 3 negatives,
Yeah.
like if you classify all them as positives, you know, you still get 97% accuracy.
So,
yeah.
I see what you're saying, but
Because you're biasing your distribution.
but we're doing the classification on the representations, right? Whereas the those negative examples were only used to get a better estimate of the mutual information. So they're completely unrelated.
But the top model is going to be a classifier, right? At the end
Classifier
of the day.
on the representations.
Yeah, for
You still have the same number of representations, no matter how many negative examples you use in your
Right.
training. Yeah.
but it has to, like, you know, tell you the difference between the representation, right?
So correct me if I'm wrong, so the negative examples have been used to create the representation, right?
Yeah.
And then you get the representations, you use equal numbers to compute accuracy. So there is no imbalance in the in computing the accuracy.
In the data that they use for classification, that's balanced.
Yeah.
Okay, that's balanced?
Yeah.
Okay.
I think you were asking about optimal values, right? Alpha, beta, gamma. So we tried an experiment where we fixed gamma to be 0.1, and then we basically created a heat map of how good the accuracy is on, it's probably CIFAR 10 or CIFAR 100. It's probably CIFAR 10 actually, because the accuracy can be this high. We created a heat map of what the optimal values should be, and it looks like when you get alpha 0.5 and beta 1, it seems to do really well, and I think when you move here, it also does just as well. So yeah, so the values we get for alpha beta are very reasonable. They're not in the order of 10 or 100. So we keep gamma fixed. Yeah.
How did you explore this space?
So we just simply did a line search. So we fixed gamma to be 0.1, and then we took different values of alpha and beta and just computed the accuracy on the classifier once you learn representations using these values in the objective.
Is there any intuition about why gamma is 0.1, like, or because of research,
we just wanted
previous research, or like, why did you set it 0.1?
So you repeat the question. So the question is, in this experiment, why did we fix gamma to be 0.1?
Yeah.
And that's because before, when we had tried a local only or a global only, that means setting either alpha to 0 or beta to 0 and the other one to 1, we found that the optimal value of gamma is 0.1 in one of those cases, but in the other case it's 1, right? So we could have tried gamma equals 1 here too, but we wanted to try one of those values because we found that to be optimal. So that's why we picked this here. Yeah. Question somewhere? Okay. We do similar plots for estimating mutual information between variables and also for the neural dependency measure. So here we found that actually it seems like the mutual information is something that's not optimal at one point, but you can have a multitude of alpha beta pairs which will give you a high level of mutual information. And then also here it looks like it's the lowest, or no, it's relatively, it's 1 almost everywhere. So it seems like a relatively flat surface, the neural dependency measure. And so one comment here is that if we see this is relatively flat, and we know that our algorithm actually did better in terms of generating independent features, as we saw in one of the previous results slides, that means that it's the deep InfoMax in general, the setup is agnostic to what the alpha, gamma, beta values we choose. It's always going to generate independent features in the representation space. Okay, so that's pretty much all the results I have, but there is some further work along this line. So this paper, Deep InfoMax, is going to be presented at ICLR next month, and there's another paper that was also accepted to ICLR, which is basically Deep InfoMax, but using it for graphs. So it's maximizing mutual information between patch representations. So you're looking at a node, and then the other nodes that are near it, so you're maximizing mutual information between that and high-level summaries of graphs. So that's a cool paper. I actually do not know much about graphs, so I can't talk too much in detail about this one, but it is being applied there. Because I think graph convolutional networks came out maybe, I think the first paper came out 2 or 3 years ago, and they've really been popular since then. So being able to do like deep learning on graphs. So
Just want to advertise that we also have a video on graph convolutional networks.
oh, nice. So what can we conclude from this? So high mutual information between the input and the representation is important, as we saw. In a lot of our experiments, we found that our model performed better in terms of generating independent features or classification on other data sets once we maximize mutual information. At the same time, we know that mutual information tends to capture global information that is shared across a whole image, and that's not necessarily always what we want to capture. We don't want to capture so much noise in our representation. So that's the whole motivation for doing a local information maximization between one part of an image and the representation. Another thing that I didn't put on this slide is that this representation learning approach is decoder free, so there's no decoder used in this, whereas most approaches like variational autoencoders and whatnot, they use decoders. So that's another thing we can do. So we found a way to basically learn representations efficiently without using a decoder network. Future work that we can possibly explore would be using multiple feature vectors as a representation. So you want to look at one, say you want to extract information from only one part of an image. You can use multiple feature vectors and then just encode that information. And also use attention. So in all our experiments and all our neural networks, there was no attention at all. It was just convolutions, fully connected layers, ReLU activations, whatever. No attention yet. But I assume that can probably improve. I hypothesize that can probably be helpful. Also, applying this to other domains. Right now, we only talked about images. That's the only thing this paper dealt with. But being able to expand this to text, speech, other modalities would be really, really helpful. And that is it.
Let's see if you have any questions.
Questions, yeah.
Well, I'm sorry, I just missed a detail in your presentation. I can't find anywhere in your paper. The detail is where the uniform distribution is mixed into. Is it the feature vector, or sorry, is it the the local patch vector or the feature vector?
So when we try to match our distribution of representations to a prior, that prior is a uniform distribution. That's where the uniform distribution comes in. Yeah.
So it's like one of the loss function.
Yes. So the third objective, which was matching to a prior adversarially, that's matching the push forward distribution to a uniform distribution.
What's the point of that?
The point of that? So from a high level, I think that okay, here's an intuition. So remember, we talked about the neural dependency measure, and you want your features to be independent, right? So usually you have your distribution in your representation space being matched to a Gaussian with unit variance, right? So you're forcing your representations to all be independent of each other. So that's how you're enforcing the independence. So here we're doing the same thing because the uniform distribution is also totally independent across all dimensions. That's the if I understand correctly, that's the idea. Yeah.
So basically, you are maximizing the entropy between different dimensions.
Yes, I believe so.
And I remember you mentioned before that you compare this to the Gaussian distribution used in adversarial autoencoder.
Yeah.
Right? But it looks like they're very different things.
Yeah, I think Amir had brought this up earlier, why we used a uniform instead of a Gaussian, and it just worked better in practice. So.
Yeah, but the Gaussian distribution in adversarial autoencoder is mixed into the latent vector directly, not an objective that you try to approximate.
And adversarial autoencoders, part of your objective is to match your distribution of your encoded representations to a prior, right? So that's exactly what we had here, too. It's basically the same.
Oh, I see.
Yeah.
So basically, it's like the approximation of maximizing the mutual information is also done through random sampling.
No, that has nothing to do with mutual information. That objective. That is only to to put certain constraints on the representations that we learned. Mutual information is the global and the local information maximization. This is just getting the representations to match them prior. That's it.
Well, I didn't get that part, but yeah.
Okay, we can talk about it later. Sure. Anything else? Any other questions?
A couple of times that this approach is decoder free.
Yeah.
What's the benefit of not having it?
Well, less computation required for one, right? Now you don't need to decode. You
have the discriminator.
Right. So I guess that is a good point. We do have the discriminator. We have multiple discriminators, but we also now we use a mutual information approach, right? So in most of the other cases, you have reconstruction loss, which is your objective. You're trying to reconstruct what you input. Right now, we're not doing that anymore. We're using mutual information.
So in VAEs, you don't really control what regime of your representation takes over your representation. You can't really control this, and you don't really explicitly, use KL, but this seems to me a more in a high, with high resolution, you have three different objective functions that both in local and both local and globally try to discriminate all these things. Did you compare with VAE by any chance?
Yeah, in some classification experiments.
See,
so the representations seem to be, yeah. Yeah. Anything else?
The Gaussian and the discriminator. So, as I remember in the adversarial autoencoders, so the reason that works is that we have some latent variables which are independent of the input and some which are dependent. So the independent ones become zero the information, then there is the ones that we want to force to be non-zero, to be carry information from the input.
Are you talking about adversarial autoencoders?
Yeah.
No, I think everything in your representation space comes from the input, but then you just force that to follow a distribution.
Yeah, but some of them could be what they call it I don't representative latent variables, and some others so they discriminate between two sets of if you have seen the factor, for example, that's the idea they use as well. So they want to force those ones to be dependent. It just forces that dependent between input and latent.
Okay. Okay. So.
Information, if they are irrelevant, it becomes zero, so you force it to be not.
Yeah. So there are a lot of works like that where they have where they're trying to learn some other sort of variable that controls for what you learn. Like for example, I think what we're talking about may be similar to this paper that I know called Deep Convolutional Inverse Graphics Networks, where you basically have this one variable that controls for one factor in your image. So it's a generative model. So you sample, and then based on how you basically change this variable, you're changing one factor in the output in your image, right? So okay. Thanks. Discussion points, and I think you actually made a good point about how when you have some information that is repeated in the image, that's noise. So I think this picture is a good example of that, right? So so you have this pattern here, right? Which is consistently goes across the whole image. But at the same time, if you were to do local InfoMax on this, we're taking all these patches, right? And that's probably like 75% of the image, and we're maximizing the information there and what's in our representation. But that's not what we want to capture. We just want to capture this one bunny. So that is one potential drawback of the local InfoMax. And the fact is that we only tried all our experiments on images like tiny ImageNet or CIFAR 10, CIFAR 100, where most of the image contains really relevant information, right? And so you don't run into problems like this there. But I'm sure if right now, if we were to scale up what we had, we'd probably see that our performance drops a lot. So that is one drawback. Other than that,
Do you have any plan to test your model on very complex data set like open images? And so it's mostly used for object detection, and then so.
Could you repeat the question? Sorry.
Yeah, I was wondering if you're having a plan to try your model on very complex data sets that they have too many different features, unrelevant features in one picture. For example, you have like.
I mentioned this in some of the results. So why is the DIM with the local only objective? Why does it actually perform better than when you have both objectives? And this was actually very unintuitive, because you'd think that when you use both local only and when you use both the local and global objectives, you're getting more information in your representation than when you use just a local only. But that seems not to be true. So local only actually performed better in all the classification tasks than when you use local and global. And it's possibly because that when you use local only, you're filtering out any high-level noise that the global maximization was going to capture. So you're filtering that out completely. So that's my guess as to why the local only algorithm performs a lot better. Local objectives to compute the representation. But the other than that, yeah.
Do you know how it performs on multi-label images, like if the image has both a dog and a cat in it?
So how would it, like what kind of representations would it build?
Right,
So,
how good it's going to represent that.
So that's a good question, because right now all the images we looked at usually contain
Single object, right?
Yeah, single objects, right? But if you were to do both, I guess using the local objective, it's going to capture the information about the dog and the cat. So in terms of the representation it's going to get, I think it will capture that information. But what do you do with that information in terms of, do you build a representation that's separate from dogs and cats? Like if you were to cluster them in the representation space, I don't know how. I don't have a feeling of how it would do on that, but I think it'll definitely capture the information. So, yeah. Any other questions? Yes.
So, because you talked about batch size by accident,
Yes.
Can I ask, so first of all, what was your compute power, and how long did you take to train time-wise?
Compute power, you meaning like?
Did you use multiple GPUs, C410?
50,000 or 60,000, something like that. So yeah, we used GPUs, of course.
The image size is very tiny.
Yeah, 32 by 32, but it's still, yeah, so it won't take as long as ImageNet, right? But it's still like, because I think one of the data sets here, STL10, that had like 96 by 96 images, so that should blow up by a factor of 3, by a factor of 9, right? So how long did it take? If I remember correctly, it wasn't too bad actually. It would take maybe a day, or even less than a day, to go end to end, just because we weren't dealing with images that were too big. So, yeah.
Anything else?
All right.
Do you have any more slides?
I don't. I'm out of slides.